Hello, welcome to Exercism's Functional February, part of the 12 and 23 challenge to learn 12 programming languages in 2023. I'm your host, Bobbi Codes, and I maintain the Clojure track at Exercism. Kind of stumbled into this role by accident. And this is the second episode of Functional February. My target audience is either programmers who are not familiar with functional programming much at all, or those who might be interested in communicating the ideas of functional program to those people, which really, that should be about everybody. So what I'll do is go over a little bit what we did last time, and I want to introduce our text, which is Grokking Simplicity by Eric Norman. I talked about this last time, and I thought it was such a great idea that I went out and bought it. Well, I didn't have to go out. And Eric is a really cool guy. He was my first Clojure career coach. It was the only time he did the program. He worked really hard to try to get me a job. It wasn't for his lack of trying. I was just simply not ready. And this was about 4 years ago, and it was sometime after that he started writing this book. And he wrote it because really there's a problem with talking about functional programming and trying to learn about it, and it's far too often very theoretical. If you look up a definition, it will say something like programming without side effects. And it's like, what is a side effect? And either that or it will be taught within the framework of a certain functional language, like Haskell would be very common. And so he wanted to make a book that was language agnostic, and all the examples are in JavaScript, which it's precisely because JavaScript is not a good language. It's not a language designed for functional programming, so that means we don't have all of the trappings of the way that language approaches functional programming. It's just a familiar syntax to express the ideas, and then we can actually implement functions like map and filter, which we covered last time. And yeah, I had to fight as much as I would ever have to fight within the context of the Exercism community to get Clojure included this month for Functional February. It was originally with the Lisps, which of course Clojure is a Lisp. But when I'm programming in Clojure, I am not thinking that it's a Lisp, really ever. And but what I am thinking constantly is I'm writing functions and passing functions to functions. And now I mentioned Haskell earlier. Haskell is the extreme example of functional language where it's purely functional, which means there are no side effects. And I just said that funny word side effects again. Um, we don't like that, and so that's why in Eric's book he explains it using actions, calculations, and data. And so side effects are actions. And here he gives certain examples. An action is something that depends on how many times or when it is run, otherwise known as functions with side effects, side affecting functions, or impure functions. And an example would be to send an email or to read from a database. That's so those are actions. And we have calculations, which are just computations from input to output, which are also called pure functions, or just mathematical functions where you have an input and an output. It will always, a pure function will always give the same output for the same input by definition. And an example would be to find the maximum number, I guess, of, say, an array of numbers, or to check if an email address is valid, I guess, with, a regular expression or something. And then we just have data, which is inert. It doesn't do anything by itself. It's just facts about events, like the email address that a user gave us, or the dollar amount read from a bank's API. It's just a number. I'm trying to get to the chat here. I want to have the chat open in case anyone wants to ask a question or something. All right, there we go. All right, so that's what functional programming is. It's programming with actions, calculations, and data. And so I've been going through this book for the past week or so, actually. And the whole first part is actually really good. He talks about what immutability means, how calculations, extracting calculations from actions, and he talks about certain design patterns. But part 2 is where we get to the stuff that's more relevant to what we were doing. And so last time we did the Hamming exercise, which let's have a little review of what Hamming is. Oh, actually, I just have it right here. It's the distance, the Hamming distance between two DNA strands is the number of characters in a string that are different between two strings. So these two strings here has a Hamming distance of 3, 4, 5, 6, 7. And this was a really good example of map and filter. And so what I did after last time is I took the last 500 solutions that have been submitted through Exercism for this exercise, and I ran them through the representer, which is a piece of tooling that analyzes the solutions and it normalizes them in order to find the most common approaches. And so I did that with this exercise, and I copied down here the most common ones. I think this one was something like 34 occurrences. And let me blow this up a little bit. So I figured it would be cool to see some of these. It's always really fascinating to see how we get so many answers to unique solutions to an exercise that you would think is extremely simple. So there's like the first operation is the map. So I think what I should do is this was the solution that we ended up with last time, and I'll just let me switch these here where I have my editor connected to a REPL, and I'm not even going to, sure, I'll define the distance function. And let's see what some of the test cases were. What happened to my okay, so here's one of the simple ones here, where it's these two strings that have a Hamming distance of 3. Wow, what's going on here? I think I need to restart my REPL because something seems weird. No? All right. Now let's see if I can evaluate this. And okay, so that returns 3. And so what I want to do is just break this down from the inside out and trace the execution. So this is our innermost form here, which is the map function. Oops. And what we're doing is mapping not equals, which we'll see what that does here. We get true, 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 because each one of those characters is different in each of the strings. Then we have filter, which filters out which one of these are true. And Of course, that's all of them because they're all true. And then the count function just simply counts them. All right, so that's pretty simple. The first line here is just dealing with, it's making it so that it will return nil if the two strings are unequal, because part of the problem specification is that it needs to handle that Hamming distance is specifically for strings of equal length. All right, so if we, when I ran the last 500 solutions, I don't remember how many there were. Let's see if, I'm actually afraid that if I get into here, it's just going to be kind of a mess. So anyway, yeah, the question is how are there so many different solutions for this simple problem? And here is one with reduce. That's interesting. But we haven't learned reduce yet. So here's where Eric will come to the rescue. Okay, so the chapter that I want to start with here. Okay, so part 2 starts with, talks about first-class functions and what that means. It's basically just that the programming that you can pass functions. Let's see if he says it here. This chapter here, functional iteration, is where he starts talking about map, filter, and reduce. And these are the functions that allow us to do things like loop over arrays without actually using a loop. And first coming to functional programming from something more imperative or object oriented, at first it's going to be completely disorienting because all the things that you would normally do with a for loop are, well, how do you even do things without mutating anything? And so map, filter, and reduce are how we replace simple for loops to loop over arrays, and we can actually see how they're implemented in JavaScript. So we have a code smell and 2 refactorings. The code smell is that there's an implicit argument in the function name. And this code smell identifies aspects of code that could be better expressed as first-class values. If you are referring to a value in the body of a function, and that value is named in the function name, this smell applies. The solution is this next refactoring. The characteristics are there are very similar function implementations, and the names of the functions indicate the difference in implementation. When you have an implicit argument in the function name, how do you turn that into an actual argument to the function? This refactoring adds an argument to your function so that the value becomes first class. This may let you better express the intent of the code and potentially eliminate duplication. So the steps are to identify the implicit argument in the name of the function and add an explicit argument. Use the new argument in the body in place of the hard-coded value and update the calling code. The syntax of a language is often not first class, and this allows us to replace the body, in other words, the part that changes of a piece of code, with a callback. You can then pass in the behavior in a first class function. It's a powerful way to create higher order functions from existing code. So we identified the before, the body, and the after sections, extract the whole thing into a function, and extract the body section into a function passed as an argument to that function. We'll be iteratively applying these powerful skills so that they become second nature. So we have Megamart. They're creating a communications team. And here there's a letter to the employees from the management. They say, hello, we now have over 1 million customers. We need to send them emails. The marketing sends promotional emails, legal sends emails relating to legal issues, business development sends account emails. And they have different purposes, but one thing in common. We need to send them to some customers and not others. That is a critical challenge we wish to face. So here is our basic function, which is using just the standard for loop. It's iterating on an array. Calling the function on that item and putting it in the new array. And the refactoring is to make a for each function. So here we have a function called emails for customers. And it takes 3 arguments here. Where instead of, it's the same 3 arguments. Okay, here Kim says, wait, this looks a lot like something I was reading about. It's called map. Map, as in what you use to find what road to take? No, not that kind of map. Map is a function that transforms one array into another array of the same length. Notice how we're taking an array of customers and returning an array of emails. That's perfect for map. Just like for each is a higher order function that loops through an array, map is a higher function that loops through an array. And the difference is that map returns a new array. The original one is unchanged. And one of the things we showed last week was something really cool you can do in Clojure is passing multiple collections to map. And we solved an exercise from Advent of Code that way. So last week we did the Hamming exercise, and this week I wanted to do another exercise on exercism that was recommended for functional February, and that was Collatz Conjecture. And this was actually one of the first exercises that I ever did on exercism back in 2018 when I was a student on the Clojure track. So this brings back memories. So it's otherwise known as the 3x plus 1 problem, and it's defined as follows. You take any positive integer n. If n is even, divide n by 2 to get n divided by 2. If n is odd, multiply n by 3 and add 1 to get 3n plus 1. Repeat the process indefinitely. The conjecture states that no matter which number you start with, you will always reach 1 eventually. I guess it's a conjecture because it's never actually been proven. You would have to just keep trying them forever, I guess. So given a number n, return the number of steps required to reach 1. And this is a solution that I did previously, but what I actually wanted to show here is this is the most starred solution in the community solutions, which the reason why I was interested in this one is because it uses reduce. And okay, so let's have Eric teach us a little bit about reduce, because this is actually a really interesting function. And it turns out that map and filter, which we learned about previously, are both actually kind of special cases of reduce. Okay, so what is reduce? Let's see where he gets into it here. Map and filter. How am I doing for time? Oh, it's about half an hour. Okay, here's he's talking about filter and all right. Reduce is the third of 3 functional tools that functional programmers rely on. The other 2 are map and filter. And so we have reduce, which takes an array an initial value and a function. And there's a concept of an accumulator, which, there's actually an exercise on exercism that is actually called accumulate, and the exercise is to implement reduce. So isn't that interesting? Let's look at this. Implement the accumulate operation, which, given a collection and an operation to perform on each element of the collection, returns a new collection containing the result of applying that operation to each element of the input collection. And so that might sound kind of complicated, but really the simplest example of reduce would just be summation. Or here we have exponentiation, where you consume a collection, and each step of the way, it's fed the result of the previous collection, the result being carried over by the accumulator. So if we have this collection of the integers 1 through 5, and an operation, which is just to take a number and multiply it by itself, then the code would produce the first 5 squares. But we're going to see in a little bit how this operation could really be anything. And a lot of things can be implemented with reduce that you would totally not think of just from the simple example of addition or exponentiation. Now, I'm not sure actually how productive it is to how much we will learn about reduce by implementing reduce, but nonetheless, it won't hurt to look at some of these. And now this one, this is funny. They're using reduce in the solution, which that's kind of cheesy. I think we should roast this person. There should be a stipulation where you're not allowed to use the function that you're trying to implement. And here's the one with just a standard loop and recur, which it's like the non-functional programming Lispy solution. And so it just loops through the collection, and each time we recur, it recurs with the rest of the collection, in other words, without the first element, and then we conj onto the accumulator the result of calling our function that's passed in with that element of the collection. Now there was another solution here which actually does that, implementing it recursively. In other words, by having the function explicitly call itself. That's what we have here. Using the familiar Lisp cons function. But this is not actually a stream about Clojure or Lisp, but it's about functional programming. So did I just, yeah. So this is the one I was, wait a minute. Yeah, okay, so I guess we've looked at accumulate enough. We kind of understand how it works. Where is, where is Eric's book? I lost my, sorry, I lost the place somehow. I can probably just search for reduce. How about that? So yeah, I wanted to talk about how map and filter are actually just special cases of reduce, and how we could implement each of them with a reduce. And you know, he might actually do that in here. Let's just see. Reduce accumulates a value while iterating over an array. Accumulating a value is kind of an abstract idea. It could take many concrete forms. For instance, adding things up is an accumulation. So is adding stuff to a hash map or concatenating strings. And so adding stuff to a hash map, that's really interesting, because we would be taking data, doing some calculation on it, and using reduce to build up a data structure, or concatenate strings together. You get to decide what accumulation means by the function you pass in. The only restriction is that it is a computation that takes the current value of the accumulator and the current element of the iteration. That function's return value will be the new value of the accumulator. And there's a really cool picture here for the more visually oriented people. Let me get a nice shot here. Oh, I need to find it again. Yeah. Oh, look at that. That's great. So you have an array of x's, 4, 2, 1, 2, 3, 4. And we have a combining function, which is just add. And we start with the initial value 0. And each step is chained into the next one. It performs add each time, and it builds up a result, which is returned as 16. The function you pass to reduce needs 2 arguments. So that would be what we usually call a reducing function. If you write a function that performs some calculation and you want to perform it on every element while using the combining function along the way, then you need two arguments, which is the current value of the accumulator and the current element of the array. The function should return a value of the same type as the first argument. And here is an example. The function count all purchases, which takes an array of customers, and it computes a total. The concatenating strings example is an array of strings that we need to concatenate together, which is also a combining operation. It takes an accumulated string and the current string from the array to concatenate. Reduce helps us combine the elements in an array into a single value, starting from an initial value. So how would this relate to map? How would you implement map where it would just perform the function on each element and put the result into a new array? Likewise, how would you implement filter in terms of reduce? It would iterate through the collection and put it in the new collection if and only if the predicate function returns true. Now there's the test function that you would pass to filter. It says to be careful with the argument order because there are 3 arguments. It can be easy to mess up the order. And yeah, this is just a little warning that each language does it differently. The second is how to determine the initial value. It depends on the operation and the context, but it's the same answer as these questions. Where does the calculation start? For instance, summing starts at 0, so that's the initial value for addition. But multiplying starts at 1, so that's the initial value for multiplication. And what value should you return if the array is empty? In case of an empty list of strings, concatenating them should be an empty string. There's actually a cool example that I'll share from my own code, which is a clone of the Mario Paint music synthesizer. And this uses the Web Audio API to play samples in the browser. And in order to make a music sequencer, we have to adjust the playback speed of the sample so that the frequency will match whatever note we want. So yeah, this is just code that loads the samples and decodes it, creates a web audio buffer, and here we go. So I have these functions add semitone and subtract semitone, which it takes, so to add a semitone, there are 12 semitones in an octave. And so if we take a sample rate of the original sample, we multiply it by 2 to the 1/12th, 2 to the 1/12th, so that it would increment it by 1/12th of the current frequency. And so here I have reduce, which it uses reduced. Here we generate a list of ones for how many semitones we want to add, and it passes it to add semitone, so that adds 1/12th of a percent of the frequency in hertz, however many times, to adjust the pitch. And so that's actually how the whole thing works. And an example of creating a data structure is the code for the Exercism representer. This was actually, I did a live stream that was like 4 hours, where I had no idea what I was doing, and tried to code the representer, which is our code normalization tool that powers the analysis tooling on the Clojure track. This isn't the code that eventually made it, but one of the steps, one of the normalizations that the representer does is variable names. It normalizes the names of the arguments that are passed in. So this is code that extracts the arg list of each of the functions. And here I wrote a reducing function. In other words, a function that will take the zipper, which represents the source code, and an arg list, and it swaps it with a placeholder name, so that I could then pass that to reduce. So we reduce, replace arg list on the original source code, and it would output something like this, which is the original function definition, and the argument names have been replaced with placeholder names. Here we have placeholder 1 for the unary arity, and placeholder 1 and placeholder 2 for the second one. Here's a cool blog post here called "Reduce My Favorite Clojure Function," and I will I'll post a link in the chat here, just because I'll be nice like that. So this is a person who really loves reduce, and he explains how In other functional languages, you'll find it named fold or fold-L. And here he starts with the examples. Now here, you see he's passing in 0 as the initial value. That is not strictly necessary, but I was actually just reading something on the Clojurians Slack that it's recommended to always pass an initial value. You might say, why is this 0 even necessary? Because obviously you add 0 to anything and it's not going to do anything. And here's using reduce to get the maximum of the values in an array, or the minimum value. And here is a simple example of, well, kind of like a little state machine. The name reduce implies that the collection is being reduced into some sort of smaller value. Now that's actually a little bit confusing because sometimes we can use reduce to make a bigger value. Use reduce to build up a structure that is much larger than the input. So because of that, I actually think fold is a better name than reduce. The name fold implies that each of the successive values in the input collection is being folded into the accumulated state, much like ingredients in a baking recipe are folded into a dough of some sort. For instance, we can return a vector containing all of the prefixes of the input collection like this. So we have a reducing function that takes the current state and an input, and it adds the state and this is our output here. So now that we know how the general idea of reduce, let's look at this solution to Collatz conjecture. And I feel like actually downloading this exercise and solving it in my editor so that we can, it's always fun to actually evaluate code on stream. So I'll copy this download link here. And let's see, I will open up a terminal. I have the Exercism CLI installed. If you don't have it installed on your machine, there's instructions here. And I'll copy this path and change into it. And open it up in your favorite text editor. Let's see how the exercise ships. And okay, yeah, so this has my previous solution here already. And here is the test suite. Steps for 1, steps for 16. Okay, so that's all right. Now I will issue this command to start my REPL. All right, so let's see what we've got going on here. Let's get the test cases over here. Collatz 1 should equal 0. First, I'll evaluate these forms here. I don't know what's going on. It's not connecting. I think I'll do it in WSL. How about that? Grab this download link again. I'm pretty sure I have the Exercism CLI here too. All right, and what I want to do is analyze this solution with reduce. Oh, it says for kicks and giggles, throw illegal argument exception by tricking Java into throwing one, which is tersor. Oh, he's doing some wizardry here. I don't even know. I'll just copy this here using reduce. He says he finds this elegant, and well, a lot of people happen to agree. 23 people. There's some good comments here too. I think these are comments from the mentors. No, that this person says I didn't know reduce. Oh, reduced. Okay, yeah, this is a special Clojure thing. We're reduced. What's the definition of reduced? Let's see. Let's go to Clojure docs. And there's reduced, and there's also reductions, which the reductions are, as you might imagine, the steps of the reduce, which actually comes in handy. There was this one time I used reductions. I think it was also in the music synthesizer. It was for making the notes of the scale. Actually, you know, I'm really curious now. Let me I was very proud to actually use reductions in a project. Oh, let's see. It's not finding it. It must not be looking through all of the history. Well, oh well. Maybe I will. Maybe I'll find that for next time. But I copied that there. But yeah, reduced. Oh, that's right. Reduce. Reduced. Reduced X wraps X in a way such that reduce will terminate with the value X. You know, I actually don't know if I ever knew about this. What does that even mean? A reduce will terminate with the value X. Suppose you want to short circuit a sum. So this takes the first 10 integers and adds them up using reduce. So that it returns the sum of the integers if less than 100. But the keyword big otherwise. Let's see how this is used in the solution. All right, now hopefully when I connect to the REPL here, it will actually work. All right, now we have working in editor evaluation. I'm planning on making some improvements to the Clojure track in the coming months. I actually want to implement inline evaluation in the online editor. So then there would be no need to use it in my editor locally. I mean, people are still welcome to, but I shouldn't feel like I have to in order to have the Clojure experience, which isn't the subject of this stream. I promised that I would focus on the functional stuff rather than the Lisp stuff. All right, so let's call Collatz 1. And we get 0. Now, I actually need to read the definition a few more times so that I can get it into my thick head what the problem is, because to be honest, I'm not sure if I'm actually getting it. Take any positive integer n. If n is even, divide n by 2 to get n divided by 2. If n is odd, multiply n by 3 and add 1 to get 3n plus 1. So let's see how that much is being done over here. Actually, let me put this over here. If n is even. So where do we test that? So first we check if n is less than 1. And if so, we throw an exception because that's an invalid value for n. And here is our reducing function. So when we want to see how that behaves, we'll just take that out and see how it works for a single value. So since n is 1, this condition here, right here, is going to be true. And so then we're just going to call reduced 1. Wait. It's not reduced n, it's reduced I. Where do we get I? the initial value this is okay, so this is I is the infinite range of integers starting with 1. So we have, if we have range, that's an infinite sequence, so we can just take the first 10 of them, and we see, so it starts with 0. So it would be reduced 0. Wait. Yeah. Let's get another test case. So the steps for 16. Divide if even. And that gives us a value of 4. So 16 is more than 1, so we go on. And it's 16 is not equal to 1. And 16 is also not odd, so that returns false. And so we hit the else case, which divides it by 2. So it would be 16. And since this is being executed repeatedly using reduce, I see that's what reduced was. When reduced reaches that value, that short circuits it. I think I get it. Do any of the viewers, does this make sense? So then it would run, we would do the same thing with 8. So just tracing this through in my head. 8 is not odd, so it will divide by 2 again. Then same thing with 4. And then 2 gives us 1, and so then it exits with reduce. Okay, so then, yeah, we need something a little more interesting. So here's an example with even and odd steps. Collatz 12. Let's trace the execution of this. So we get 9. Let's see how that happened. So 12 divided by 2 gives us 6. And then 6 divided by 2. Okay, so that's the first one where we have an odd number. So then when we run it with 3, this returns true, odd 3. And so then our result is this. Where it multiplies it by itself and increases the number, which gives us 10. which then gives us 5, which then is multiplied by 3, right? Yeah, that's the problem. And then 16 we saw before, right? That was the previous test case. Yeah. And so then we have all of those. Then steps for, what is this number? 1 million? Yes. Which is a huge number of even and odd steps. But you know what? I want to try using reductions, because reductions is a really cool function. It's another one that people just sometimes forget exists, and it comes in handy in really cool place. I really want to find the one example that I had, but you know what? I think I need to actually wrap this up. It's been about an hour and 17 minutes. So what did we do today? We read a bunch of Eric Norman's book, which was pretty cool. If you're interested in a book to learn about functional programming that's not tied to a certain language and doesn't get bogged down in theory, it's really the first one that I know of that is at least that is written this well. And we saw how to implement map and filter in JavaScript, and how map and filter are actually special cases of reduce. We saw a bunch of different examples for reduce and looked at the solution using reduce for the Collatz conjecture. In other words, the 3x divided by 3, the 3x plus 1 problem. And thanks for joining us. Until next time on Functional February of the Exercism 12 and 23 Challenge. Be safe now, everyone. And happy functioning.